Good evening to you, my followers and friends. I'm back again this evening to consider a very fascinating concept in macroeconometrics. Recall that the period I actually talked about the violations of the classical least square regression assumptions, I made mention of a term called heteroskedasticity. So this evening I will actually be looking at the meaning of this term called heteroskedasticity, how to dictate the presence of heteroskedasticity in a time series studies, and how to resolve the problem of heteroskedasticity. Please stay tuned to my channel as I make view or as I review this fascinating development. The word heteroskedasticity refers to disturbance whose variances are not constant in a given model, and the term is a sum of two Greek words, heteros and skedastic. Heteros refers to difference on unequal, whereas skedastic refers to spread, and it's likely to occur mostly in cross-sectional data. The basic OLS assumption states that the error term must have an equal spread or constant variance. Constant variance of the error term differs across observation, but assumptions require that the error term must be homoskedastic. So basically, in time series study, it is actually expected that the disturbance terms must have an equal variances. But whenever time the variances of these disturbance terms are not equal, it then means that the assumption of homoskedasticity is violated. Then we now conclude that there is the presence of heteroskedasticity. This implies that heteroskedasticity as a concept in macroeconometrics is the opposite of homoskedasticity. So basically, the violation of homoskedasticity is referred to heteroskedasticity. Okay, there are two methods in detecting the presence of heteroskedasticity in a time series study. We have the formal method and the informal method. Okay, starting with the informal method. The informal method refers to the use of graphs, the use of line graph, the use of two-dimensional graphs to actually explain the presence or absence of heteroskedasticity in the time series, a regression. We have three graphs here. The first graph expresses the presence of homoskedasticity because the distance between the graphs are equal. We have the constant variance in this graph because there is no presence of heteroskedasticity because the distance between this graph is equal to the distance between this space. But the second and the third graph as exposed here shows the presence of heteroskedasticity because we are either having an increasing variance or we're having a decreasing variance. So we can now conclude that heteroskedasticity exists when there is increasing variance or when there is decreasing variance. But when the variances are constant and equal, we have the presence of homoskedasticity. The formal way of actually identifying the presence of heteroskedasticity in a time series study will refer us to look at the equations of Bruchberg and Godfrey, required to look at what Glacier LM text estimated. We're also going to look at the equation of Harvey. We're going to look at Conker-Bassett. We're going to look at White text. We're going to look at Park LM statistics. So these are estimations that actually could be used to identify the presence of heteroskedasticity. So basically, let's start from a normal linear regression equation. The heteroskedasticity is actually built on the residual of a normal single or multiple linear regression. What do I mean? What I mean is that heteroskedasticity or the equation that form heteroskedasticities are always developed from a normal regression equation. From what we have here in equation 1, you have equation 1 which expresses the linear relationship amongst the variables so explained. We have y as the function of x1, x2, x3, and we have the error term. So if you want to actually look at it from the perspective of forming a heteroskedasticity equation, then we are going to make this error term the subject of the formula. So too many studies, too many authors had actually made this error term subject of their formulas to derive the heteroskedasticity models. For instance, the first in the list of authors, the first in the list of approaches, the first in the list of methods that considered the squares of the residual, the square of the error term as the dependent variable is Bruce, Godfrey, and Pagan. Godfrey and Pagan actually regressed the square residual on the original regressor by default. That means that in Bruce Godfrey equation, the residual or the error term is the dependent variable, and the square root of the error term is the dependent variable, while other explanatory variables remains the way they were. Then in Glacier LM statistics, Glacier actually regressed the absolute residual on the original regressor by default. The absolute value of the residual, the absolute value of the error term was regressed on the original regressors by Glacier LM statistics as its own test of heteroskedasticity. Then we have another equation that was built by Harvey. Harvey actually regressed the log value of the square residual on the original regressor by default. This is another form of heteroskedasticity equation that was built by Harvey. Harvey regressed the log value of the square residual on the original regressor. That was Harvey's equation. Then Concord-Bassett actually looked at the residual of a regressed residual on the dependent variable itself. Recall that the dependent variable of the previous equation we actually saw as the model equation was yt. But in a situation where the error term becomes a dependent variable and the dependent variable becomes an explanatory variable, then that is what we call the Concord-Bassett equation. Then we also have the White test. The White test actually regressed the square residual on the cross product of the original regressors and its constant. So there is a cross multiplication of the variables of the variables of interest, like what we have s2 and s1 and s2 being multiplied together. We also have the Park LM statistics. The Park LM statistic equation actually expresses the log value of the square residual or the log values of the original regressors by default. So these are various estimation procedures, the various test statistics used in actually establishing the presence or absence of heteroskedasticity in any time series regression. Then to solve the problem associated with heteroskedasticity, there are also methods. There are also different methods used in solving problems relating to heteroskedasticity. Okay. The first way to solve problems relating to heteroskedasticity is what they call the functional form, while the second method is called the general least square, while the third one is what they call the weighted least square approach. The functional form, or changing the functional form of an equation, requires the researcher to actually look at the unit of measurement of the variables and see how he or she could actually manipulate or to change the unit of measurement of the variable. For instance, if you are modeling, or if you model a log-log scenario and you observe that in your log-log scenario there is a problem of heteroskedasticity, what you are expected to do is to actually model a linear scenario or a linear model to see if the problem of heteroskedasticity will actually leave the work. So looking at what we have here, we have a log-log model when the dependent variable is logged and the independent variable is in level. At that level there may also be issue. So if you will find yourself in a situation where you are having heteroskedasticity and you actually want to resolve it, the first thing to do is to actually look at the unit of measurement and see how you can be able to modify it. So basically, let's go to our eView portal. Let me teach you how we can resolve the whole of this computation using the eView. Recall in our last class, in our last ARDA class, I actually adopted a study approach where we considered the impact of stock market variables on economic growth in Nigeria. And by stock market variables, we talked about market capitalization, the number of deals in the market, and the value of transaction. We also introduce interest rates into the model. So if we are looking at it from that perspective, our GDP becomes our dependent variable. So if we estimate an ARDA test, we are going to actually look at how to generate the heteroskedasticity result and also how to have the problem solved. So if you want to generate an ARDA result, like I have said previously, you go to quick, you move on to estimate equation, you come over to the equation estimation box, you specify your model. We have the log value of ROGDP, we have the log value of MCAP, we have the log value of NDIL, we have the log value of veteran, and we have interest rates. I think this was the equation I actually used the other time in ARDL estimation. I'm using if it's 10 today, my lag will remain lag 2. I'm choosing lag 2, fixed regressors, restricted constant. Okay, this is our ARDL result. To actually check if there is a issue relating to heteroskedasticity, you go to view, you maneuver to residual diagnostics, you move on to heteroskedasticity. You will be exposed to this box. You leave it at Bush-Began Godfrey text. These are other texts I made mention of previously. You leave it at that. Without changing any other thing, you click OK. You will be exposed to a result that looks like this. I'll copy it neatly to a Microsoft Word where I will interpret. The result that looks like this. This is my Microsoft Word. This is a Microsoft Word, and this is my result. This is my result. This is my result. If you look at this result, you take a critical look at this result, you observe that there is a problem with heteroskedasticity. The residual of this particular distribution is not equal, or the spread is nothing to write home about. Let me make it bold so that you will be able to look at it critically. This is the result. This is the result. Okay, this is the result. Your attention should be within this first section. If you look at this result, you observe that the p-value of F statistics is 0.0036. The p-value of the observed R square is 0.0160. The p-value of scale explained residual is 0.0000, which means that there is a problem with this result. This result is having issue with heteroskedasticity. There is a full-blown heteroskedasticity problem in this result. You cannot present a result that has this kind of problem. So the next thing to do is to actually decide on how to resolve this heteroskedasticity problem. And how to resolve this using the formal way is to actually look at the functional form of the equation. Yes, this model is actually a log-log model. And since we actually looked at a log-log model, the next thing to do is to actually remove all the logs from the original equation and re-estimate the model using the raw data without being logged. With that, I believe that the problem of heteroskedasticity will be solved. But as a researcher, while doing this, you also have to explain your methodology that the reason why you actually remove the log attached to the original variables is because of the presence of heteroskedasticity that has forced you to actually remove the log. So having removed the log from the original estimation, I will now re-estimate the model. Having re-estimated the model, we have gotten a new model. I will go to view. From view, I will maneuver again to residual diagnostics. From residual diagnostics, I will move again to heteroskedasticity. I will still leave it at Bush-Pagan-Godfrey test. I hit OK. Then I will be exposed to another result that looks like this. This is what I got this time. This result is better than what I got previously. I will copy it neatly to a PowerPoint or to a Microsoft Word for actually identification and interpretation. So this is the new result I just got now. This result is different from the previous one because the p-values of this result is different from the p-values of the previous one. The F statistics is smaller. The p-value is 85%. The observed value square is also smaller. The p-value is 86%. The scale explained SS is actually smaller. The p-value is 5%. Although this result is very close to 5%, but 0.057 approximately is 6%. So we can now relatively say that the problem of heteroskedasticity has actually been resolved using the functional form. So this is one way to resolve the problem relating to heteroskedasticity. In my next video, I will actually explain how to use other methods to resolve the problem relating to heteroskedasticity. Please stay tuned to my channel and enjoy yourself. Thank you and God bless you.